Good afternoon and good evening.
Hello.
Hi,
Hello, good afternoon.
good afternoon, and it's good afternoon, everyone. Welcome to today's webinar on the application of XGRIDS tech and products in the AEC industry. I'm Mindy, and I'll be your host for this session. As we know, the AEC industry is undergoing rapid transformation, and the technologies like mobile scanning, reality capture, and 3D data integration are playing a crucial role in how projects are designed, monitored, and delivered. Today, we will explore how S-grade solutions and the products are being applied in point cloud registration, renovation projects, and digital workflows, as well as some like AEC application scenarios such as corridors, buildings, and tunnels. And today we have two speakers. And first is Christian. Please say hi to all the audience here.
Hello, everybody.
Yeah. Later on, we will have introduction and a presentation. And Colt, please say hi.
Hi, hello everyone. Nice to meet you.
Yeah. So at first we may have Guido, and however he met some emergency today. So and I feel sorry. We wouldn't have him as our speaker, and Colt will also bring about a very good speech talking about S grades applying in the tunnels. And then firstly, we will have introduction for every speaker. Christian is the director of 3DS Scan, and today his topics is about the registration, registering X-rays point clouds with terrestrial laser scans using Lexa Studio, Pinpoint, and Cloud Compare. And Christian, you can here you got a mic to have all the presentation and your introduction.
Thanks a lot, Mindy. I'm going to share my screen. Yeah. Can you see my screen? Yeah. Okay. Let's share it. Okay. Yeah. Hello again. My name is Christian Rochner. I'm founder and managing director of 3DS Scan. We are an engineering company based in Aachen, Germany. And yeah, my background is rooted in geography and remote sensing. And yeah, we are involved in various industries, and our main websites are, of course, 3DS Scan and realitycapturetraining.com. Yeah. So what I would like to talk about with you today is the overview and methodology of point cloud registration, especially how we can register LXL L2PRO data, for example, with terrestrial laser scans. And we will have a look at Pinpoint. Pinpoint is a tool which we use internally a lot for registration purposes, may it be terrestrial laser scans or, as today, SLAM-based point clouds, which can also be processed in Pinpoint. Also, we will have a look at Cloud Compare, which is, some of you might know it already. It's an open source tool, which is very interesting if you are involved in processing point clouds. And also there we have the possibility to register point clouds. Yeah, a few things about that later. So what do we do at 3DS Scan? We are a service provider for surveying and engineering, and we are in Aachen since 2016 in our office. Our work mainly involves photogrammetry projects, kind of large-scale projects of corridors with 100 kilometer, for example, but also laser scanning projects, close range, but also quite big projects. And in the last years, Gaussian splatting became a thing where we are involved in. And as I'm a geographer myself, I'm also a lot involved in GIS and related software and workflows. So on the one hand, we're a service provider. On the other hand, we're a training center, of course, for all the XGRIDS products, in case you need advice for the software or how to handle the hardware, how to capture data in a nice way. but besides the XGRIDS products, we are also an EPIC partner. So we are doing trainings for Reality Scan, Twinmotion, Unreal Engine. And Unreal Engine, of course, goes very well with XGRIDS Gaussian splatting, as you might already have heard that. Yeah, besides that, we also are a vendor for DJI products and do a lot of trainings for all kind of drone workflows, drone surveying. And we are also partner of 3DF Zephyr. And of course, we also offer GIS trainings, ArcGIS, QGIS. That's the software we use in-house. We also offer consulting and support for all these, for all these software products or for the hardware. And we have an online shop where we are offering hardware and software, of course, all the XGRIDS products, DJI products, and software we also use in-house as EPIC software like Reality Scan, Twinmotion, Unreal Engine, and SCASA Pinpoint, which we will have a look at today, and also 3DF Zephyr. Yeah, so let's have a look at point cloud registration. What are we talking about here? The definition for point cloud registration is it's the process that aligns two point clouds by spatial transformation into a certain kind of coordinate system. So, for example, we have a terrestrial laser scanner. This might be a Leica or a Faro scanner. There are many brands around. We take, let's say, 10 or 20 scan setups. And if you want to bring these scans together, the process is called registration. Some scanners already have a GNSS device in the field or have a pre-registration already in the field so that you can base your exact registration on an already existing course registration. What do we need as an input? As I said, multiple scans taken from different viewpoints or at different times. This can be from one laser scanner, but you can also mix it, especially in pinpoint. You can take Faro, Leica scans, mix it with Lixil scans. So this is kind of a universal registration tool. The output, if you import multiple scans to, for example, pinpoint or cloud compare to bring them together, is a transformation or a set of transformation that brings them into one big alignment. So you don't have 50 isolated single point clouds, for example. Instead, you get one consistent point cloud. And this is mainly done by rotation, translation, sometimes also scaling or deformation of the point cloud itself so that the two pieces or several pieces can fit together in a perfect way. The goal here is to minimize the difference or the distance between two corresponding point clouds, which of course need some certain type of kind of overlap. For types of registration, I would just say a few words here. We differ rigid and non-rigid registration. Rigid registration, means that we only added rotation and translation. Yeah. So the shape of the overall point cloud will not be changed. A non-rigid registration allows local deformations. So these are the two different types of registration. Sorry, I will say a few words about that later on. Here on the screenshot, you can see a setup of, let's say, 100 scans, all in relation to one another and aligned, in this case, in the Leica software, which comes with the scanner. Yeah, point cloud registration. You can. There's a very good example for point cloud registration by comparing it to solving a puzzle. So visually speaking, a scan can be imagined as a puzzle piece. And if the registration parameters between the scans are known, one point cloud can be transformed into the local coordinate system of another point cloud. You can see a 2D example of that in the figure 1 on the left side. The general goal of puzzling is to assemble an image from individual pieces together. This is comparable to assembling the individual point clouds of an object in terrestrial laser scanning. To combine individual pieces of point clouds, a single piece can be rotated about the origin of its local coordinate system, or shifted along X and Y axis. These three parameters are also referred to as degrees of freedom. I hope that's the correct English translation. Analogous to puzzling, registration is a sequential process in which the last scan is attached to the previous or the already registered scan. So I think that's a very nice explanation how this works. So you translate and move one scan until it fits to the other one. That's would be like a manual registration, and then you can go from there by using some automated registration like the ICP. The accuracy of the registration results depends normally on two factors: the accuracy of the used sensor, of course, and the propagation of uncertainty in the calculation of the value. So that means if you scan a long hallway and each registration, so one point cloud to the next, has a slight error in it, this means this error can add up to a quite severe error over the distance. Good example is if you scan hallways or featureless corridors in some buildings without any control points or targets, then you might end up with an error propagation which deforms the point cloud in a way which we can see on figure 2. The accuracy, of course, can be supported or improved by using targets and control points. So then you have a known variable which supports your registration in a very safe way. Just a quick overview over the different types of registration. As already mentioned, we have the manual realignment, which is the simplest but most time-consuming method. So you take the point cloud, you move it over the axis, you move it where you want it to be, and this is the automated process. So you shift and rotate the point cloud over X, Y, and Z axis, and try to move it as close as possible to an already registered or to your base point cloud. And from there, you can do a fine registration, for example, the ICP, which we also will cover in a minute. So that's very common to, if you have a set of point clouds, to make sure you move it in the same spatial region and try to pre-align it manually. Then we have the target-based registration. The idea here is that you place artificial targets like spheres or checkerboards or some reflective prisms in the scene before you scan it. And the targets are automatically or manually detected in each scan. And the center coordinates can be used for control points or can be measured in form of a control point. A transformation, translation, and rotation will be computed to align the scans. Pros: very accurate and robust, works even with limited overlap, because it's it just makes a very, very robust registration without with a very limited probability for error propagation. Cons: it requires physical setup. It's a lot of work you need to do before, and that means you are much slower in the fieldwork. Then we have the feature-based or geometry-based registration. The idea here is to use natural geometric features like edges, planes, trunks, or building edges, identify them, and do the alignment or registration over these features. No artificial targets are needed here or used here. And features are detected and matched across the scan, and then a transformation is created to align back to the previous scan. No need for targets. It's more automated, but less accurate if the environment lacks a certain distinctive geometry, or if it has a lot of occlusions and very low overlap. Then we have the cloud-to-cloud registration, which is a very common, I think the most common one. Very typical example here would be the ICP, iterative closest point registration. So you can directly align point clouds to themselves or to their neighboring point clouds based on point distances. How does it work? The ICP registration uses an initial guess, so you already need to move the point clouds very close to each other and try to roughly align them manually, for example. From there, you can refine the translation, rotation, and minimize the point-to-point distance of your two point clouds. It's an iterative process, so Then we have hybrid or multiple methods. This is also very common. You do not only use one method, we also use a lot of registration in the field with GNSS or with targets, and then we use cloud-to-cloud and manual registration sometimes. So you can mix all the different methods here. Yeah, and of course we have the registration by GNSS and total station control for georeferencing, for example. So you can use known coordinates to make sure that your registration is in shape and everything aligns perfectly. This is especially useful in large-scale surveys, and when combining multiple scan stations, I would also advise to use this kind of registration. Of course, again, this can be used in combination with ICP or with manual registration. Yeah, a few more words about ICP, because this is one of the most common algorithms, also in Cloud Compare, and you can find it. What is it? Widely used algorithm for aligning two overlapping 3D point clouds without any targets or feature detection, simply by cloud-to-cloud or point-to-point distance calculation. As mentioned, initial guess is needed here. You have 2 point clouds roughly aligned, and from there you can execute the ICP algorithm and compute the transformation. Strengths are here that it uses the full overlapping geometry instead of just a few targets. And you can reach millimeter level accuracy after good pre-alignment, of course, depending on the scan and on the point clouds you are using. Weaknesses, well, it needs a decent starting alignment, which you can base all further steps on. Otherwise, it can converge to a wrong local minimum. And this is something you should keep in mind. What kind of software can be used to do the this kind of registration? Well, that depends, of course, on the hardware. Normally, all scanners come with a certain kind of registration software. Regal has its own, Leica has its own, Faro has its own, but you also have universal things like Pinpoint or like Cloud Compare, where you can simply drop in E57, or as for Pinpoint, you can also use native Leica raw data, so no need to have any Leica software to register the point cloud. I mean, it's a Leica software, of course, now, but So, let's have a look at Pinpoint. What is Pinpoint exactly? What can it do? Because it can do much more than the registration process only. Pinpoint is, on the first hand, a cleaning and registration software, but you can also create 3D models directly in the point cloud. That's the Pinpoint modeler module. So you can draw in 3D, and also it has some automated features, so you can automatically set a wall and detect walls or doors and windows, and therefore you can create very quickly like an easy 3D model. And this one can be used to extract very exact 2D floor plans directly based on your laser scan data without the need for any other software. We will have a look at the first two steps: registering imported scan data using 3D snapping and auto align, and clean and filter the scan data using various tools. So let me jump into the software. I hope this works as intended now, as sometimes live demo is a bit difficult, but this looks good. I go in the full screen mode. So here, this is the user interface of Pinpoint, which you are currently seeing. The process usually starts by importing scan data. Yeah, so you can import, as I said, Leica raw data for BLK and RT3 360. This is fully supported, so you can directly copy it from the scanner and start registering here. But you can also import E57 format, recap projects, and ASCII formats. So pretty cool. So you can basically get all the point clouds you produce from laser scanning. You can just import them. Once the scans are imported, so I have a little example project here with some terrestrial laser scans, TLS, outdoor and indoor, and the scan is added, or we will add the scan with L2PRO data, XGRIDS data in the inside. Yeah, that's the setup here. Before we start registering, you can set a point filter in Pinpoint, which is pretty cool. You can select a certain range, radial, vertical, and horizontally, how far your scan should be used, or the range where your scan should be used in Pinpoint. You can detect isolated points and small objects, and save them in a clipping feature, which can be activated or deactivated here. But you can also detect ghost geometry and bake cleanups finally into the point cloud. I won't execute this now because this will take a while. I already did this. Sorry, my mic muted. So this is usually the first step before we start the registration process. Then you have your scan positions imported. Let me move a bit closer here. So we can see this is the area of our office. And as mentioned, the plan is to add up this room here from LIXIL data, because the terrestrial laser scans were only done through the hallway and through the rest of the building, but not every room was captured. So we will use E57 from LIXIL Studio and align this to our existing point cloud. How do we export from LIXIL Studio to do this? This is the related project from LIXIL Studio. Once you imported your raw data and executed the SLAM algorithm to create your point cloud, you can export the point cloud here as a structured E57. So this is pretty cool, because then you can handle the scans like terrestrial laser scan positions. Yeah. Also, you could export to RCP. Also quite a nice feature. In our setup here, we exported it to E57. And this is basically these 4 scans, which you can see on the side here. So now what do I have to do to move a scan and bring it to its position? You can see in the data tree here that the scans are activated to show, but I need to activate this little button here. So I can move the point cloud in the 3D space. So now I can simply grab the point cloud and move it near the actual room. We'll zoom a bit closer here. And now I will do the manual registration. It's already in the correct orientation. So I just need to move the scans a bit over to the right. Oops, sorry. And try to overlay them with our terrestrial laser scans like this. So as good as possible. We can, of course, also check that. If I just try to look at the point cloud in this way, or I can do a section view. And from here, I can see if the point clouds are roughly where they should be. Yes, that looks good. We can see here, this is the room. So in this case, the manual rough registration is successful. And what I need to do now, as the terrestrial laser scans are already registered, and I want to move the L2PRO E57 to the existing registration, I will select the indoor scans, select the, I will select all scans for indoor and also for the L2PRO. Sorry, my selection does not, now it's working. So we'll do it like this. So we'll select all the scans that I want to bring together and then simply execute the snap scan function like this. Takes a while, and now the scan positions all move together. And also I can see in the statistics, I can see the deviation between the scan positions here and also the overlap. Yeah. I can execute this process several times. So I would also advise this to do this several times. So do it again. Oh, sorry, that was the wrong button, but now I snap the groups. Yeah, that was the wrong button, sorry. Snap scans. And now we can see it's an error of 7 millimeters, 5 millimeters, 4 millimeters, 4 millimeters, and an overlap in percentage. So pretty easy. First, bring the scans manually to their position, then execute the snap scan function, and that's it. Besides that, maybe 1 or 2 more features, and then we will move on. There are some very nice cleaning tools. As if you work with different laser scan data, the data can become quite noisy sometimes. So it's very good to have some nice functionality to clean it. One thing we can do, I will create a cleanup here, or click on, I will create a new cleanup. And from here, I have cleaning tools, a lasso, like this sphere, but also these 2 tools here. So this one is a filter. I can select points behind a certain plane. So if I click on it and I define 3 points on the wall, the software automatically detects the plane. And now I can move the plane inside the wall, click on the left mouse button, and now I selected all points which are located behind the wall, or behind the window. Of course, I delete now the office as well. I could now take the lasso tool and deselect it, of course. This would be possible. Deselect is shift. So this would be possible as well. Pretty cool tool. And maybe one more thing, you can also delete objects in a nice way. For example, if you have a car or people running through your scan, you can draw a polygon around a certain object. For example, this chair here is this tool. Confirm by double clicking. And now I can define how high I would love to clip. And now I selected all the points belonging to this chair, and now I could simply delete it. Pretty cool tool, pretty nice to use. So in case you have any questions about this, feel free to contact us. Okay, so that's a very simple example for registration in Pinpoint. Now let's move back to the presentation. And so from here on, just as an example, you could go and do the 3D model, extract 2D floor plans. And this is pretty cool if you have one scan with a terrestrial laser scanner and add up all the different rooms with the SLAM scanner to one unified point cloud. Cloud Compare, on the other hand, you might already have heard about it. is a free and open source software for 3D point clouds and mesh processing. It runs on Windows, Mac OS, and Linux. And the key features here are importing, exporting point clouds, convert them into different formats like E57, LRS. You have registration tools, manual, ICP, fine alignment, and so on. You can create or calculate cloud distances. For example, the name Cloud Compare already might give you a clue. It's mainly a tool to compare different point clouds with each other and compute changes or distances. But you can also segment, filter, decimate your point cloud, visualize it, annotate it, or use one of the tools to process, for example, forest data, forest LiDAR data, and create like a tree cataster or something like that. Why use it? Well, it can handle very large data sets, also on a smaller machine. You have an active community, many plugins, and it's really a must-have for everybody involved into surveying, photogrammetry, LiDAR, and point cloud processing. So let's have a look at Cloud Compare. Oh, I hope working. Yeah, okay. So I imported here terrestrial laser scans on the right and Lixel SLAM E57 laser scans here on the left. In the user interface, you have a DB tree where you can see all the content of your project. You can switch between scalar field and RGB color, just to mention that. And you have a few tools for registration. We have match bounding box centers. So this is usually the first thing I do if I get scan data, which might be in different coordinate systems. I try to match the bounding centers so they all are laying over each other. And then you have an algorithm which allows you to pick points to align the point cloud. So you can pick 3 mutual points in both clouds you want to register, and then the clouds will be registered according to your entry. And we have the ICP fine registration here as well. This requires, as mentioned, that you do a manual translation before, move them roughly over each other, and then execute the ICP. I will show you this in a second. So I will move, let me check the scan number 3 to scan number 0. How can I do this? I select the scan. I activate the translation or rotation tool. Here I can move my point cloud over a certain axis, and I can also lock axis, for example, XYZ axis. And now I try to roughly overlay them. Yeah, of course, you can also transform the point cloud in any different way here. So roughly overlay them as good as possible to make sure we are in the same height. You can use this kind of previews here and see. Oh, yeah, maybe that was a bit too quick. So gonna see again from the side to see if we are on the same height. That looks quite well. That's enough overlap or enough accuracy to do an ICP registration. And now I would simply select these two, scan 3, scan 0. I go to the tool section, registration, and now I can do the fine registration ICP. I already matched the bounding centers manually, so no need to execute this now. And also you can match scales here, for example. If you have a scan from a LiDAR device and, for example, a photogrammetry scan from the same object, you can scale them here. So now I click on ICP. Now you can see one point cloud is the one that will be aligned. In my case, it's the scan number 3. And I can choose the reference here, which is the scan number 0. You can swap them here just so you have control which point cloud will be moved to the other one. Then you can set a number of iterations, 20 actually quite a nice value, and an RMS difference, which is set to 0.00001 meter. And final overlap set to 100%. If you want to, for example, register photogrammetry data as well, you can also adjust the scale of your objects here. So now I press OK. And in a second, point clouds be matched in a very nice way. So here we see the final RMS, which is 0.8 meters. Please keep in mind we're using SLAM data here, and we have the transformation matrix here. And this is the way how you can execute this alignment. Just to give you another idea, the other option would be to use the align point pair picking tool. So here you can, sorry, I need to select 2 point clouds. Let me, for example, take these two here. So registration and align point pairs. And now I can say which one I want to align. For example, this one. And now I can pick points, mutual points in both point clouds. Maybe I will just do it as an example here. So I can click on targets or on, very easy to identify exact points. And from here, you can then register the 2 point clouds according to your entries here. Minimum is 3 points. The more points you do, the better. And if you also have georeference points, no problem. You can also georeference your scan by setting these points and align the point cloud. So that's it from my side. Small introduction into registration and possibilities with SLAM data and terrestrial laser scan data. I can only enforce you to try Pinpoint. It's a very, very cool tool. So if you're involved into registration and into scanning buildings or whatever, please try the demo. It's very nice. And Cloud Compare is for free in any case. So just give it a try. Thank you very much. That's all from my side.
Hello, Chris. Hi, thank you. Hi, Chris. Thank you for the presentation. So yeah, is there any question?
Yeah, we got one from that comment area. From Pablo, there is a question: how and when do you save the data? Is there a history log? Christian, you are mute. Yes. Yeah, here in the chat area, there's a question. How and when do you save the data? Is there a history log? Yeah. So the question, the answer is yes, right?
Yes, there is. In Cloud Compare, you could clone the data before registering. That's something which is recommended. So you clone your data set, switch off the original one, and then you register with the cloned data. And in Pinpoint, in any case, you can just go back if your registration is not correct.
Yes, great. And thank you for that presentation. That one is an excellent one. And Pablo has already got his answer. And to answer all of you, the webinar will be recorded and sent to your email, your registered email. And I think for this session, and the question has been answered, and we will move on to Code's presentation. He will talk about the XGRIDS applied in internal scenarios. And if you have any questions about Christian's presentation, you can also leave in the comment area. We will answer them later. And then let's give the mic to Cote.
Hi, everyone. My name is Colt. Today, I would like to share use case, and how, if for the AEC industry, how to use XGRIDS to scan tunnels. So my presentation will be divided into 3 parts. So in the first part, I will introduce a very challenging scenario, how to scan long, narrow, and dark tunnels. I will introduce this case from 3 aspects: the preparation, scanning, and post-processing. Then later on, I can quickly introduce how to scan long and repeated tunnels. And in the end, some users want to get coordinates for their point clouds, and we can discuss about whether we should use RTK or ground control point. First, the scanner I would recommend to use is the XGRIDS L2PRO. This scanner has 3 types: 16 channels, 120 meters, 32 channels, 120 meters, and 32 channels, 300 meters. The relative accuracy is around 1 centimeter per 100 meter, and the absolute accuracy with RTK is around 3 centimeter. And then 16 channels means 320,000 points per second, and 32 channels means 640,000 points per second. And it has a IP ratio of IP54, and each battery can work 90 minutes. This scanner integrates visual scan and LiDAR scan. I have used it to scan tunnels many times, and this is a very reliable and robust scanner. Okay, now we go to the first part. How to scan a long, narrow, and dark tunnel. So this is the tunnel we scanned together. This tunnel is around 300 meters long, and this tunnel is very narrow, average at 1 meter in width and 2 meter in height. And originally, it is very dark. The narrowest place in this tunnel is only 0.5 meters wide and 1.5 meter high. There are 2 big challenges. The first one is the narrowness and darkness of this tunnel can easily lead to slant drift. And then because it's quite narrow, so it's not suitable to use big scanners. So if we need to scan some equipment in the tunnel, so then a small portable scanner would be the better solution. And the second challenge will be, in this tunnel, there are many fire doors in the tunnel, so it will influence the slam as well. And in order to scan this tunnel, we brought 3 scanners. So 1 terrestrial laser scanner, 1 very big backpack laser scanner, and the XGRIDS L2PRO. And then in the end, only XGRIDS L2PRO made it and successfully built the model. So this is the workflow. The first step will be to evaluate the environment and do a plan. This is very important. In order to scan this tunnel, we brought some LED lights, and we brought a door wedge, and we brought some sticky marker. First, I went through the complete tunnel and got familiar with the environment, and I predefined the important areas that I needed to spend more time later on. And then I use a door wedge to hold all the doors open, because because in this environment the slam is very sensitive. If we move doors in the tunnel during scanning, it will influence the slam. And then later on, we turned on all the lights in the tunnel, and we placed some LED lights on the ground on very dark places. this is very important. This is very important for this scenario. I will quickly introduce the visual SLAM and the LiDAR SLAM. So as we can see here, the XGRIDS scanner has like here, this is a camera for visual SLAM, and this is the LiDAR. So for visual SLAM, it needs to work in an environment with abundant light, with very good light condition. And the advantage of visual SLAM is the working distance. So it can, even if it's very narrow places, as long as the light condition is good, it can work well. And then for the LiDAR SLAM, it's very accurate. But the disadvantage from LiDAR SLAM is it needs at least 0.5 meter distance so it can work. In this tunnel, sometimes 0.5 meter distance doesn't meet it doesn't meet the requirement. So if we add more lights in the tunnel, the visual SLAM can greatly help with the SLAM. And then next part is to predefine connection points if needed. So why we need to think about this issue? Is map fusion in this scenario necessary? So I will give you an example. As we all know, the longer the scanning time, the longer scanning time may lead to a bigger cumulative error of SLAM. So during a scan, so if we have a loop closure, or we have a crossover, or we use GCP with absolute coordinates, it can improve the accuracy of the SLAM. But in my scenario, these three are not possible. So in the first scan, this is a cross section of the tunnel. Actually, in the first scan, I tried to scan in one time. So I went all the way here, and then the SLAM drifted here. So I know, okay, one scan cannot handle this challenging environment, and I start to use the map fusion. I decided to add connection points here because this place is a relatively open area, and there are more sufficient feature points. So this makes it a very good place for to aid connection points. But for example, here, this kind of narrow place is definitely not suitable to aid connection points here. The next step is the scanning. So during the scanning, I deliberately held the L2PRO above my head because then I can aid the scanner can collect more feature points from the front and also from the behind. I try not to use my head to block the behind. And then during the scanning, I try to walk slowly and reduce vibration. And then in a second scan, I went all the way to the connection point, point 1. I placed the scanner on the ground. The scanner faced forwards. I add a connection points in the Nixel goal and then stop the first scan. And then without moving the scanner, I start the second scan at the same place and add a connection point with the same name. So for example, connection point 1. And then I lift up the scanner. The scanner still face this direction forwards, and then I slowly go backwards for around 10 meters. So the 2 point clouds have 10 meters overlap, and then I start to move forwards. So in this way, there is enough overlap, and then when the scanner faces the same direction, it helps with the map fusion. And then because it's a very narrow place, I don't use a closed loop. If a closed loop here will probably make the slant drift. And then after scanning, I check the real-time point cloud in the Nixel Go. I make sure, okay, there was no drift and no tilt, and then I can end the scanning. And then during the post-processing, I choose the map fusion function. So I choose the point clouds, and then here it's very important we choose the narrow thin mode here. So it will help the Nixel Studio to increase the map fusion successful rate. And then later on in the coloring, I choose internal camera and I choose dynamic point cloud removal, and then I start to process the data. And then after processing, we can check the point cloud quality. And if we need to draw bin or CAD model later on, then we can export RCP or LAS or E57 for further processing. And for customers who like to draw a bin model or CAD, so if there is enough light during the scanning, so we can use a 3D Gaussian splatting model from XGRIDS as a reference. Because if you have the experience, we all know that sometimes it's hard to identify an object or an equipment in a point cloud. So the Gaussian splatting will greatly help us identify the objects. But in my project, the Gaussian splatting, the quality of the Gaussian splatting was not good because the light condition was still not very good. Then the second scenario would be how to scan long repeated tunnels or hallways, for example, like this one, because this tunnel, this hallway lacks feature points, so it would be a nightmare for SLAM. But we can solve the problem, so we can prepare some cartons or tapes and bring some portable LED lights if possible, if needed. Still, we walk through the tunnel and then have a look, and then we can place LED in dark places, and then later on, we can place cartons in places with insufficient feature points. So we use cartons to increase feature points for the point cloud, for the SLAM. And also we can like stick tape onto the walls, so to aid the feature points for the SLAM. And then in the end, in some projects, our like the customers also want to aid coordinates for the point cloud, even though there is an underground tunnel. And this is possible. So it depends on the project. So for example, for this project is underground tunnel, and it depends on the length of the tunnel. So if this place is less than 100 meters, then it's relatively easy. So we can start the scan from above, turn on the RTK, and then go into the tunnel and then climb up. As long as it's less than 100 meters, the Nixel Studio is able to process the data and perform the coordinate transformation. But if it's over 100 meters, using RTK for coordinate transformation in the Nixel Studio will fail, but we can use GCP on the ground. So we can add 3 GCP on the ground, and then we can use straps. We can use a strap from XGRIDS. We can actually wear this strap the other way around, and then we can after scanning the 3 GCP, and then we can climb down the tunnel and then climb up, and then we perform a coordinate transformation with ground control point. It can still work. Yeah. And thank you. This is my presentation today.
Thank you, Colt, for this presentation. And we all know that tunnel scenarios for that mobile scanners are really challenging scenarios. And this these solutions and scanning techniques are really helpful. And is there any questions about this part? You can also leave in the comment area. If we don't have any more questions here in this session, we will send the recorded version to all of your registered emails. And if you got any further or additional questions, you can also let us know through the email or from any of that comment area. Then we have one from Lion. Do you ever use the XGRIDS scanners for creating the GCP coordination points? I'm not sure whether this is for Colt or Christian. Both of you can say their insights about this question. So, Christian, do you have any experience like this? Christian, you're on mute.
Sorry, no, we never tried this actually to collect GCPs. Maybe Kay has some more insights on that.
Mm-hmm.
Lime, I don't know what you mean. So you mean whether we can use GCP for coordinate transformation, or?
I think it means if you can really measure ground control also with the L2PRO. That's how I understand it.
So firstly,
I think so, yeah.
So firstly, we do have this function for use a ground control point base to make some control point on the ground or on the walls. And you can use that ground control point to do the map fusion as well as the coordination. So that's the function itself. And especially in some relatively large scale cases, we do as GCP to do the alignment and the coordination. Yeah, hope that helped with this question. And another question from Pablo, how does Lexogo react in the tunnel? You mentioned losing fixed first then, and is there a color coding on the real-time display? What does usually yellow, what if red? Yeah, I think that question goes to Colt.
Yeah, I think when we scan a tunnel, as long as the them walks, then we can see the trajectory very clear, and it will not like the position, the current position will not like fly around, and like the color, I think in a Lixo Go means the elevation of the point cloud, so it doesn't mean the point cloud quality.
Yes, exactly. So in the Lexo Go, we will use different color to show the different heights of the points, and you can show in a relatively large scale case, especially the turtles, you can see different heights of the points. And in Cloud Compare, you can choose different color to show different different level of information. Okay, so we got another one from Lion. Can you use the scanners, for example, the L2PRO, to collect the exact coordinates of a GCP, or you use a separate piece of equipment? Thanks all.
Yeah, I think we can.
I think that one is about.
Definitely, we can use L2PRO to collect the coordinates. So, for example, we define a GCP, and then we can turn on the RTK in the L2PRO, and then we can go to the point, add GCP in the Lixo Go, and then later on we can check the coordinate of the GCP in the point cloud.
Yeah, exactly. We provide a different module of the RTK. We got a big RTK module and a small one, and those two serve for different scenarios. The big one will have better precision, especially in internal scenarios. Yeah, I think most of the questions have been answered today, and if you have more, please leave that in our comment area. And yeah, we got some additional information. The Lions issue is about always there is a poor RTK base station system in Ireland, so the RTL can really connect properly. I think that one should be talking about the RTK modules, like the signals things. And in China, we in some areas of China here, we also have some very similar problems. And for the surveying team, they may use some like the total station to help with that for some certain points, and we use GCP to do the coordinate.
I would recommend to use the survey grade RTK from XGRIDS. The signal is quite good.
Yes. Another one from Sherwin. Does XGRIDS follow any specific standard and a requirement on how to capture an indoor space and obtain an area as well as strata boundaries? I think this one can be answered by both of you two.
Hi, Chris, you can go first.
Well, I mean, that always, I mean, there's of course some guidance on how you need to use the scanner to capture indoor spaces, but I think mainly you just need to try and to practice it. And of course, there's some standard recommendations how to do it. Some examples of projects that were captured, but in the end of the day, you just need to find your own workflow and see how you can work comfortably with the scanner. Yeah.
Yeah. I would say indoor space is a general concept, because indoor can be a small place or a huge place, or it can be an relatively open area, or very challenging place with narrow tunnel with narrow hallways, or like a lot of glass. So it depends on the environment, but I would say if you want to have relatively high accuracy, and so I would suggest to have closed loop and also have some crossovers during the scanning. Yeah, or GCP to increase your accuracy.
Yes, from my experience, I follow a standard like firstly I do a scanning class plan and a road plan first, and then during that road plan I will do a general scan at first, and then to some specific area scans to follow that general scans. So for me, I also use different heights scans in some indoor cases, especially for those complicated one, or some factory with some very big equipments, or some pipelines. If you want to get that pipelines, we also recommend you to use some extension pole to get that pipelines under the roof. So to say that like serial scanners is quite easy to get on hands, but if you want to get really precise result, there must be some techniques. And thanks for Coates and Christian, they share their scanning techniques as scanning masters, and they really mastered the scanning techniques well. And I must say, I also agree with Coat that it really depends on the environments that you want to scan, and you adopt them more, you will get more knowledge, or more solutions quite fit for your scanning scenarios. Hope that answer could help. And if we don't have more, we will close this session to an end. And thank you for all of your attendance and consideration. And thank you for that sharing. And we will see you in another webinar. If you got any recommendation or suggestions for all the next topics, please leave us messages and we will answer them quickly. Thank you all.
Okay, thank you.
And
Thanks a lot.
thank you.
Thank you. Yeah, bye-bye.
Bye.
Bye bye. Bye bye.